So like I said, now I'm going to begin this process. I think I'm gonna do this for probably several different streams. I'm not. It depends on how it goes. So obviously, I might decide to just stop very soon to do other things. But I think I'm gonna, just because it's easy and something I can do on stream that is gonna also help me everywhere else. I think that's probably a good idea to do this project here. And today I'm just gonna read the chat that I had with GPT here to organize the project. But what I'm gonna try to do is to like build all these systems using Turing Complete, the game. So build the circuits in the game on the component factory probably first, then build more complex systems on the sandbox after I build each component factory. And the idea is to try to translate the knowledge from that I learned from lectures and stuff like that into actual circuits, so I can clarify all the concepts and everything. And most likely I'm gonna use GPT across the whole process. So probably gonna chat with GPT, then try to build stuff, and then keep iterating until I build everything that I wanna build. I'm just gonna wait to see if it's streaming on the here. I'm gonna read the chats.
So I'm planning on building a computer from scratch, or building systems from scratch at the hardware level, using the Turing Complete game to do it. That way I can put into practice things I'm learning theoretically. In order to do this, I'm going to use the sandbox and component factory options on the game. Based on what you know about me, can you help me develop a markdown that outlines each project you think I should be doing, in sequential order, and why? The idea is to clarify all points of confusion that I discussed with you on several different chat threads across our history. I will do this by manually building the circuits myself. I prefer having greatest level of clarity as possible, and I plan to have a markdown that looks something similar to this pattern. #1. H1. 1D 2D Wave Propagation Simulator, FDTD style goal. Build intuition for waves, EM acoustic, reflection, transmission, dispersion, boundary conditions, milestones, research and scope, equations, discretization, stability. Implement 1D wave solver plus visualization time domain. Extend to 2D grid plus colorized field plots. Animation, add sources absorbing boundary PML, and simple material contrast. Write short notes linking to sampling, aliasing, and lithography optics, where I can mark each box with a V after I complete the project. That way everything is organized and I can build components and systems in a way that each system makes the next one easier to build, and allows me to compound skills exponentially over time. This is the idea. The logic gates I have available on the component factory and sandbox are 1-bit, delay line, 1-bit memory, 3-bit decoder, 1 and 2-bit decoders as well. Full adder, adds 3 bits and outputs result in carry, XNOR, XOR, NOR, NAND, or 3 and 2 input ones, and 2 and 3 input ones. Switch not, on off, always on and always off 8-bit, 8-bit delay line 8-bit counter, 8-bit register, 8-bit mux, 8-bit switch, byte splitter and byte maker, 8-bit constant value. Less signed, checks if one input is less than the other, less unsigned, checks if one input is less than the other, equal, checks if two inputs are equal, multiply, div, add, neg, asher, arithmetic shift right, 8-bit rotate left and 8-bit rotate right, 8-bit shift left and 8-bit shift right, 8-bit XNOR, XOR, NOR, NAND, OR, and, not now there are 16-bit, 32-bit, and 64-bit gates, that are basically the same as these ones but for using more bits. Then there are I/O and custom as well, I/O. HDD persistent memory, sound, 256 customizable tones and pitch control. Bit indexer, extracts a single bit from a wire. Configurable delay, add a configurable amount of delay, useful for delay debugging or controlling the latency of the latency RAM. Byte indexer, extracts a byte from a wire. Halt, stops execution with a custom message. Clock, placing the clock will divide ticks into 2 phases. The clock is red in the early phase and green in the late phase. RAM, dual load RAM. RAM with an extra load pin. Latency RAM, lowers delay by having save and load take several ticks to complete. RAM, low gate cost but slow memory. ROM, read-only memory. Outside the sandbox, fast RAM, fast but high gate cost memory. Sandbox only network, handles network connection, time, Unix time in microseconds. Keyboard, records key presses from your keyboard. Bidirectional, bidirectional pins from 1 bit to 64 bits. Can circumvent certain circular dependency errors. Input pins from 1 to 64 bits. Output pins from 1 to 64 bits. Switch, from 1 bit to 64 bits, only outputs if the switch pin is on, green, probe wire probe and memory probe. Display a value on your custom component or in the program editor. And finally, the custom gates, register plus, DEC, cond, ALU. So I would also like to know if you think I should rebuild some of these components from scratch, or build for the first time since some of them I didn't build. The game just provides it, like most of the I/O ones. Or if I should just use them. My priority is to have the greatest understanding I possibly can over the entire computational process of modern computers. Without any simplification, I want to understand things as deeply as I possibly can, to the extent that I can. No shortcuts unless logical and necessary. And I want to work on this in a way where it becomes synergistic with everything else that I'm building. My plan is to livestream myself building these systems on Turing Complete, so I won't mention anything that I'm building on this thread or project, and would prefer you did the same, because I will share these messages with my stream. I will read them while live streaming and build the systems with you for help as well, so can you help me clarify and organize everything so we can start building? Remembering. 1. Build the markdown list style of things to build, with check marks. 2. Decide what to build and why, goes hand in hand with first topic. 3. Decide whether or not to build some of the components that the game already gives from scratch instead of using theirs, so I can understand how they work in depth. 4. Decide whether or not to build on the component factory first or sandbox first. I'm thinking probably build subsystems on the component factory first, then use these subsystems on the sandbox where we build more complex systems. Also, it's important to note that the game allows exporting the schematics designs as Verilog files. These also opens up opportunities to do different things while live streaming as well. It would be interesting to know what do you think about this. The main reason why I'm doing this now is because it's supposed to allow me to have something to live stream while I deeply learning things that are relevant to the personal projects and businesses I'm building off stream. That way I optimize my time as I work on all of these things simultaneously. So please let me know what do you think about this. Below is a single coherent build graph, expressed as a markdown project ledger, ordered to maximize causal clarity, abstraction integrity, and skill compounding. This is not a curriculum. It is a dependency-respecting construction sequence where each artifact explains the next one mechanistically. I separate what must be rebuilt, what can be treated as axiomatic, and where component factory versus sandbox is appropriate. No motivational filler. No shortcuts except where abstraction collapse gives no new information. Metastructure, read once. Component factory, equal to place where abstractions are forged. Sandbox, equal to place where abstractions are composed under load. Rebuild anything that collapses multiple mechanisms into a black box, for example ALU, register plus. Hides timing, arbitration, or state transitions. Do not rebuild. I/O that depends on host integration, keyboard, network, time. ROM. HDD semantics beyond interface contracts. Exporting to Verilog is not optional. It is the escape hatch that forces semantic precision and lets you compare your mental model against real synthesis constraints. Phase 0. Time, state, and causality, foundation. Point 1. Explicit clocking and phase discipline. Goal. Make time a first-class object instead of an implicit assumption. Build. Two-phase clock discipline using delay lines plus probes. Milestones. Construct explicit early-late phase separation. Demonstrate race versus latch behavior. Create a clocked invariant checklist. What may change per phase? Why? Every later confusion, pipelines, hazards, reduces to violations of phase discipline. Factory. Rebuild provided clock? No, but wrap it to expose phases. Point 2 to 1-bit storage taxonomy. Goal. Understand why registers exist, not just how to use them. Build. Level-sensitive latch. Edge-triggered flip-flop master-slave. Explicit enable versus load semantics. Milestones. Show metastability via delayed feedback. Demonstrate write after write collapse. Prove equivalence between latch plus clock gating and FF. Why? Registers are not memory. They are time barriers. Factory. Rebuild 1-bit memory. Mandatory. Phase 1. Arithmetic is signal flow. 1.1. Adder lattice 1, n. Goal. Remove adder magic. Build. Half adder. Full adder. Ripple carry. Carry look ahead, manually, small width. Milestones. Measure carry propagation delay. Observe fan out versus depth trade-off. Why? All Alice, address generation, and speculation rest here. Factory. Use provided full adder. Rebuild first, then compare. 1.2. 2's complement as a structural invariant. Goal. Understand signedness as encoding, not metadata. Build. Negation via invert plus add. Subtraction as addition. Signed versus unsigned compare circuits. Milestones. Show overflow versus carry divergence. Validate less signed versus less unsigned manually. Why? Control flow, exceptions, and speculation depend on this distinction. Factory. Rebuild compare gates? Yes. Phase 2, data path primitives. 2.1, multiplexing, decoding, and selection. Goal. Clarify selection versus routing versus naming. Build. Mux from gates. Decoder-driven selection. One hot versus binary control. Milestones. Demonstrate illegal states. Compare gate cost versus control complexity. Why? Instruction decoding, register files, and issue logic all reuse this pattern. Factory. Use provided decoders later. After rebuilding once. 2.2. Register file, structural, not logical. Goal. Expose a read, write asymmetry, and port contention. Build. Multi-register bank. Separate read ports. Write enable arbitration. Milestones. Show WA. War hazard structurally. Demonstrate multi-read, single write constraint. Why? This is where UO begins structurally, not algorithmically. Factory. Use register plus. Rebuild first. Phase 3. Control as a program. 3.1. Microsequencer, hard control. Goal, show control as explicit state evolution. Build. Finite state controller. Instruction step microcode, even for trivial ISA. Milestones. Visualize control flow as state graph. Add conditional transitions. Why? Before pipelining, you must see the sequential skeleton. Factory. Use con gate. Rebuild equivalent logic. 3.2, instruction decoder. Goal, map symbols, control signals, without magic. Build. Opcode decode. Control word generation. Milestones. Explicitly list all control lines. Prove no unused combinations. Why? Later, superscalar decode is just parallelizing this. Factory. Phase 4. Memory is latency, not storage. 4.1. Memory interface contracts. Goal, treat memory as a delayed function, not a variable. Build. Load store handshake. Valid ready semantics. Latency RAM integration. Milestones. Stall logic. Structural hazard demonstration. Why? Caches, speculation, and UO are all latency hiding strategies. Sandbox. Rebuild RAM internals. Treat as black box with timing. Phase 5. Pipeline the world. 5.1. Classic 5-stage pipeline. Goal. Make hazards unavoidable and visible. Build. ID, X, Mem, WB. Pipeline registers. Simple forwarding. Milestones. Raw hazard reproduction. Stall versus forward comparison. Why? This is the minimal environment where timing errors become logic errors. Sandbox. Factory components reused, registers, muxes, decoder. 5.2. Precise exceptions. Goal, understand rollback requirements. Build. Exception detection. Pipeline flush. Architectural state restore. Milestones. Prove single retirement point. Why? This constraint defines reorder buffers later. Phase 6, out of order is bookkeeping. 6.1. Reservation stations. Goal, decouple issue from execute. Build. Operand tagging. Ready busy tracking. Milestones. Show wake up, select logic. 6.2. Reorder buffer, ROB. Goal. Separate execution order from commit order. Build. Circular buffer. Commit logic. Exception rollback. Milestones. Demonstrate precise exception recovery. Why? UO is not magic, it is disciplined state deferral. Sandbox. Phase 7. Memory hierarchy and coherence, optional but pure gold. 7.1. Simple cache. Goal. Make locality explicit. Build. Direct mapped cache. Tag plus data plus valid. Milestones. Mispenalty propagation. Phase 8. Export, compare, reflect. 8.wog export. Goal. Collapse simulation fantasy into synthesis reality. Milestones. Export core components. Compare against known RTL patterns. Identify mismatches in timing assumptions. Why? This is where understanding either survives or collapses. Final direct answers. Rebuild versus use provided. Rebuild, adders, ALU, register file, control, pipeline logic. Use as is, I/O, RAM internals, ROM, HDD. Factory versus sandbox. Factory, anything that introduces a new abstraction. Sandbox, anything that composes greater than or equal to 3 abstractions under timing pressure. Streaming synergy. This plan is stream safe because each artifact is self-contained, visually inspectable, and narratively causal. If you follow this order, confusion does not accumulate, it collapses. There is one big problem I forgot to mention. How do I validate and debug as I build? On the standard levels they have tests that you can run, but on the component factory and sandbox I don't think there are any tests. Also I really like your list and explanation, but I don't want to stop at just memory. I was also thinking about doing things like GPU, CPU. We will do the pipeline, but I was aiming at building a real 64-bit CPU. Just simplifying the memory, but staying faithful to the concepts and principles. Network requests and NI cards. The full pipeline from process to communication. Digital signal processing and analog conversion systems. And all of these things. Basically to build from scratch all systems where I have the greatest amount of uncertainty or clarity from scratch. And also it would be nice if you could provide a markdown style text just with the project names and a checkbox on the left side so I can easily figure out where I'm currently at. And also some context in the end of the file so I can just copy and paste the entire markdown file to open a NEW thread with the context or so I can upload it as a project file. In order for you to easily understand where I'm currently at, can you provide this markdown file outlining checkbox, system name and then context in the end for clarity of execution? After we have this markdown I will start live streaming and start working on the projects on a separate chat thread on this project. I'll answer this in 2 layers. First principles, how validation debugging must work when there are no built-in tests. A single copy-pastable markdown file with a clean checkbox project list, names only. A validation doctrine section at the end that explains how you test everything in practice. A short execution contract so future threads inherit the same assumptions. No fluff. This is about making correctness observable. Validation and debugging, the core problem. When you leave levels with tests, you are no longer solving puzzles, you are doing hardware engineering. The only viable strategy is to replace external tests with self-checking structure. There are 4 invariants you must enforce everywhere. A. Observability is not optional. If a signal cannot be observed, it does not exist. Rule. Every subsystem you build must expose internal state, registers, flags, queues, control state, FSM state, phase, valid ready, timing, cycle counters, phase markers, mechanism in Turing complete, probes on internal wires, not just outputs, explicit debug outputs, temporary ports, cycle counters built from registers plus adders, phase tagging, early late, carried alongside data. You are not cheating by adding debug wires. You are doing what real silicon designers do with scan chains and logic analyzers. Deterministic micro tests, you write the tests. Instead of a global test harness, you build micro harnesses. For any component. Drive exhaustive or structured input sequences. Capture outputs into registers. Halt with an error code if invariant breaks. Pattern. ROM or counter generates test vectors. Comparator checks expected versus actual. Halt gate triggers on mismatch. This turns the sandbox into a self-verifying machine. Invariance examples. Never test does this work for X. Test properties. Conservation, no value appears, disappears. Monotonicity, counters, pointers. Mutual exclusion, one-hot signals. Ordering, commit order versus execute order. Idempotence, replay safety. Most bugs in pipelines and UO machines violate invariance long before they violate outputs. DIME local reasoning only. Never reason across what happens later mentally. Instead, snapshot state every cycle. Assert what must hold in that cycle. Treat every stage as a pure function plus registers. If correctness cannot be established cycle by cycle, it is wrong. Differential validation via Verilog export. This is your ultimate backstop. Export components, and compare structure against known RTL patterns. Check for unintended latches. Check combinational loops. Reason about critical paths. You are not validating performance. You are validating semantic intent. 2. The Markdown project ledger, copy-paste. Below is exactly what you asked for. Checkbox plus system name only. Ordered for dependency and clarity. No explanations in line. Context plus validation doctrine at the end. Markdown copy code Turing complete. Systems build ledger. Final alignment check. Validation problem, addressed structurally, not hand-waved. Extended scope, CPU, GPU, DSP, NIC, ADC, DAC, integrated coherently. Markdown ledger, copy-paste ready, checkbox only list. Context block, sufficient to bootstrap a new thread or upload as project metadata. Factory, sandbox workflow, preserved. When you start the stream, the first real work is phase 0.1%. If time is not explicit, nothing else is real. Obviously, I will still need to chat with you each step of the way to clarify things and get necessary help for building everything. Thank you for helping, by the way. Just one more thing to clarify before opening a new chat thread and starting this process. What do you think I should name these series on YouTube for live streaming it? Obviously, I don't know how much time it will take to do each thing, so the idea I have is just to increase the number after each stream, and also put the name of the project I'm currently working on. So something that is easy to understand, allows to gain traction, and also is easy to write after each stream, and allows me to easily name the stream based on the current project or system I'm currently working on. I can either increase the number of the series after each stream on the name, or I can increase the number based on the project, for example stream name or current project part hashtag number, or stream name, or current project, or part hashtag global number. Let me know, what do you think is the best way to name each stream so I don't have to spend a bunch of time thinking about this before every time I'm going to stream myself doing this. You want a naming scheme that is 1. Cognitive cost per stream. Stable over years, doesn't break when scope expands. Readable out of context, someone drops into episode 137 cold. Indexable, both by humans and YouTube search recommendation. This is a systems problem, not branding. First principles constraints. There are 3 independent axes you are trying to encode. Series identity, what universe this belongs to. Local work context, what system you're building now. Temporal order, where this sits in the overall process. Trying to compress all 3 into one overloaded number or ad hoc phrasing is what creates friction. So the rule is 1 axis, 1 token. Never multiplex meaning. The correct abstraction. You want 1 global monotonic index and 1 local semantic label. Not per project numbering. Not reset counters. Not episode X of Y. Why? You will revisit old subsystems later, debugging, refactors, extensions. Per project numbering breaks when work interleaves. Global numbering gives you an immutable time axis. Recommended canonical form. Decomposed. Series name, constant. From NAND to silicon. Global stream index, monotonic. 40-second. Current project, subsystem. Register file, multi-read, single write. That's it. No part, no episode, no extra punctuation. Why this dominates your alternatives. Compared to less copy code stream. Problem. Part implies bounded sequence, false. Resets mentally when project changes. Viewers can't tell global ordering. Compared to closer, but part still implies local segmentation. Ordering information is visually de-emphasized. Why global number first matters. Humans scan left or right. Putting 40-second early gives immediate orientation. Is this early or late in the journey? Can I safely jump in? This matters for retention without you optimizing for it consciously. Series name recommendations. Pick one and freeze it. You want something that signals depth. Signal's bottom-up construction is not gimmicky. Will still make sense when you're building NICs, GPUs, ADCs. Strong candidates. From NAND to silicon, best fit. Computers, built honestly. Reconstructing the machine. Silicon from first principles. Avoid. Learning X. Building a CPU. Hardware 101. Those locks go prematurely. Minimal decision rule so you never think again. Pick one series name. Maintain one global counter. Title format as always. PHP template. No exceptions. The moment you start hesitating or renaming for clarity, entropy wins. One last system level note. Your ledger already acts as the semantic backbone. The stream title is just a pointer into that graph. That's the correct separation of concerns. When you're ready, open the new thread with the markdown ledger, the current checkbox, the current stream number. We proceed deterministically from there.
Well, the microphone wasn't working. So what I was saying is that the hardest part is gonna be to, on the beginning, is gonna be to validate. Because on the normal levels, obviously you can run the solutions and you can see if it's working or not. But so on this component factory, I'm not really sure I'm gonna do this. So you were saying that I should use the probes here, but obviously I'm gonna need another, a lot of help to figure out how to do this. So I'm going to open a new thread and copy paste this. Actually, I think that I'm gonna edit it as a file, probably better, and then I just put it on the chats. The thing is, I don't really understand, obviously, like how does it work on the behind the scenes on ChatGPT? How do they add that to the context? So I'm never really sure if it's gonna capture the file or not. But I think I'm gonna try like this. Just gonna upload the file of the markdown. And then after each project that I finish or after each threads, I just re-upload the file, probably. Let's try. something else that I wanted to see. It told me to build the register again, but I'm not really sure if... Yeah, so this one you can go into the implementation, so... But it's using this... This one is from a level, so maybe I can go back to the level. The problem is that I can't read on the... I have to go one by one in the playback schema, or... Like on the level thing there. So... I don't remember building this memory probe either. So yeah, play campaign. Let's see if I find it. Maybe is this one? Yeah, this would be, I think this is the register. So saves and loads a byte. Then obviously the 16 is gonna be a collection of this connected to the bus probably. Maybe it's still a good idea to try to build it from scratch again. So I can reuse this one. And then instead of the output would be some logic, like some bus, and then some logic to determine which one is active to the address. That's basically what the address of the RAM is. It's just a number that determines what row you're reading or writing from. I think I'm gonna ask that to ChatGPT as well. I want to try to build it in a realistic way, obviously.
You're at the correct place to slow down and be precise. Phase 0 is not a component, it's a semantic contract about time that every later component must obey. If you get this wrong, everything above it becomes hand-wavy, and you'll never be sure whether a bug is architectural or just temporal ambiguity. I'll answer in layers. 1. What an explicit two-phase clock discipline is, mechanistically. 2. How to realize it concretely in Turing complete. 3. How to verify correctness without relying on faith. 4. Where Verilog export fits, and where it doesn't. No branching suggestions beyond what's structurally required. What explicit two-phase clock discipline actually means. At first principles level. A two-phase clock is a causal separation mechanism. You are enforcing the invariant. No state element may both observe and influence another state element within the same phase. Concretely, time is partitioned into repeating cycles. Make full copy. Code F1, evaluate, sample. PH2, commit, update. Or equivalently. Scale copy code phase A, combinational logic reads old state. Phase B, state elements latch new values. The key properties are non-overlap, PH1 and PH2 are mutually exclusive. Directionality, information flows only PH1, PH2, never PH2, PH1 within the same cycle. Visibility discipline, writes in PH2 are not visible until the next PH1. This is what prevents combinational loops masquerading as state. Accidental transparent storage. Time travel bugs, I wrote it and read it in the same cycle. In other words, you are not building a clock signal. You are building a temporal type system. 2. How to realize this in Turing complete, concretely. 2.1. Do not start in the component factory. The factory is where abstractions get frozen. Phase 0 must first be observable, inspectable, and breakable. Start in a sandbox circuit. 2.2 represent phases explicitly, not implicitly. You need two global wires. Eng copy could phi1. Phi2. With the invariant. In a copy could phi1 equal to not phi2. Phi2 equal to not phi1. But more importantly, only one is high at a time. You can realize this minimally as a single clock input, a toggle flip-flop, combinational decoding into two phases. However, early on, manual control is better. One input pin for PH1. One input pin for PH2. A hard assertion that both are never one simultaneously. Why? Because you want to see violations. 2.3. Enforce phase discipline, structurally. Every stateful element must be split conceptually. State storage. Write enable gated by phase. Example invariant. PGSQL copy code a storage element may only latch when fit2 equal to 1. A combinational path may only read storage when. This means no latch, FF clock directly by time ticks. Every enable path and dead with phi2. Every read path is combinational but conceptually belongs to phi1. You are not trusting yourself to use it correctly. You are making incorrect usage impossible. 3. How to verify correctness. This is the core question. You do not verify this with example programs. You verify it with invariants and adversarial probes. 3.1. Build phase violation detectors. Before building latches, build monitors. Examples. Overlap detector. In a copy code error equal to phi1 and phi2. Route this to a red LED or halt gate. Write during read detector. For a storage element. In a copy code error equal to readnable and write. This should never fire in a valid design. These are not debug aids. They are part of the architecture. 3.2. Build a single bit storage cell as a test object. Do not jump to registers. Build 1 bit of storage. Explicit D, Q. Write enable gated by phi2. Then test pathological cases. Toggle D during PH1, Q must not change. Toggle D during fit2 with write disabled, Q must not change. Enable write only during PH2, Q updates exactly once per cycle. If you cannot break it, you don't understand it yet. 3.3 times skew tests. Manually do illegal things. Briefly assert both phases. Assert neither phase. Glitch phase ordering. Your circuit should either halt or expose the violation via probes. Silent failure is disallowed. 4. About exporting to Verilog. 4.1. Verilog is useful, but not at the beginning. Exporting to Verilog early gives you syntactic confidence, some timing linting. It does not give you semantic assurance about phase discipline, protection against accidental transparency, clarity about causality. RTL simulators assume you already know what a clock means. You are still defining what a clock means. 4.2. Where Verilog export does make sense. Once you have a proven two-phase storage primitive, phase monitors, invariant probes, then export only that primitive and check. Are there unintended latches inferred? Are enables cleanly edge level separated? Does synthesis preserve your intent? At that point, Verilog is differential validation, not primary truth. This aligns with your phase 15 note, export and reflection, not definition. 5. The correct first steps distilled. In strict order. Create explicit phi1, phi2 signals, manually driven. Build overlap and misuse detectors. Build a single bit phase correct storage element. Actively try to violate its assumptions. Only then freeze it into a component factory abstraction. If you skip step 4, you're building mythology, not machinery. Final grounding principle. You're not adding a clock. You're making time a first-class inspectable object. Once time is explicit, everything above it becomes mechanical instead of mystical. I'll be very explicit and mechanical. 1. Will this be reused by other components? Yes, but not as a clock generator in the usual sense. What you are building in phase 0 is temporal infrastructure, not a datapath element. There are two distinct artifacts you must separate. The phase discipline itself, global contract. Stateful components that obey the discipline. Only, 2, should be widely reused via the component factory. If you immediately package 1 as a reusable black box, you lose observability and you will not know whether later bugs are violations of the contract or bugs in the contract itself. So the correct split is sandbox. Define and validate the phase system in the open. Component factory. Freeze phase respecting primitives, latch, FF, register, that assume phi1, phi2 already exist. In other words, phi1, phi2 are global rails, not local subcomponents. 2. What pH1 and pH2 actually are, no abstraction. They are 1-bit control signals that encode which half of the cycle we are in. Nothing more. Phi1 equal to 1, read, evaluate phase. Phi2 equal to 1, write, commit phase. Invariant. Java copy code if ion, XOR, phi2 equal to 1. Phi1 and phi2 equal to 0. They are not data, not clocks, not 64-bit, not buses. They are single-bit wires used exclusively for gating. 3. How to build PH1, PH2, minimal, concrete. 3.1 First version, recommended, manual phases. This removes all ambiguity. Inputs. Phi1 in, 1 bit. Phi2 in, 1 bit. Internal logic. Overlap detector, Phi1 in, and Phi2 in. Outputs. Phi1. Phi2. Phase error, optional but strongly recommended. Rules. Phi1 equal to Phi1 in. Phi2 equal to Phi2 in. If phase error equal to 1, halt or light an error, LED. This lets you step phases manually. Violate rules on purpose. See failures immediately. This is not reusable logic, it's a laboratory. 3.2 Second version, optional, later, derived phases from a toggle. Only after you understand the first. Minimal implementation. 1. Flip-flop, phase. On each tick, phase equal to not phase. Decode. In a copy code Phi1 equal to not phase. Phi2 equal to phase. Still single bit. Still explicit. Do not skip to this version first. 4. What logic gates you actually use? For phase 0, the gate set is trivial. Not. And. Optional or. XOR for assertions. You are not building arithmetic. You are building causality enforcement. No 64-bit gates anywhere in phase 0. 5. How other components will use this? They do not call the phase component. They connect to the rails. Every stateful primitive you later build must have inputs. Phi2. Writenable. D. Output. Q. And the only place storage updates is in a copy code effective write equal to writenable and Phi2. Reads are purely combinational and conceptually belong to Phi1. You do not pass Phi1 into everything, you respect it by construction. 6. What goes into the component factory now versus later? Do not put this in the factory yet. Phi1, Phi2 generator. Phase assertions. Global discipline logic. Do put this in the factory once validated. Level sensitive latch, Phi2 gated. Master slave FF, built from 2 latches, opposite phases. Register with enable that cannot write outside Phi2. Those components assume PH1, PH2, exist globally. That's the correct abstraction boundary. 7. Why this answers your reuse concern. Sandbox schematics are for defining laws, discovering invariants, breaking assumptions. Component factory is for freezing laws into matter. You are currently writing physics, not engineering products. Once physics is correct, reuse becomes safe. 8. Absolute checklist. To start building, no ambiguity. Create 2 1-bit inputs, Phi1 in, Phi2 in. Wire them directly as Phi1, Phi2. Add Phi1 and Phi2. Error. Prove to yourself you can violate it. Keep this circuit open while building your first latch. Only after that, extract primitives into the factory. If you do this, phase 1 arithmetic will feel boring, which is exactly what correctness looks like.
What I don't understand is if I think that the component factory is supposed to be like a building where you build the building blocks that you use on a bigger design. And then the sandbox use a bigger design, but I don't understand if there's no input and output here, how is this supposed to work? I guess the only thing that makes sense is that you're supposed to use this bigger components here to connect everything, and then you visualize what's happening on the system. I think that's the only inputs and outputs here are these gates that simulate the peripheral endpoints of a normal hardware. I'm not sure if I have this on the component factory. And there is no of those other systems there. I'm pretty sure I'm supposed to do this on the and the hard part about doing this with ChatGPT is the loss of information between threads. That's the most annoying part. Because like obviously I have to understand what exactly is suggesting me to do. I'm not really sure if I understand very well what he wants me to do in the beginning. I think it's kind of like a clock, but something but slightly different. And I was saying to use 1 bit as well input, but there is no, or maybe there is here. So here it goes from 1 bit to 64. So I guess it would be something like this. Then it was telling me to use this XOR and AND.
Good catch. This is a real constraint, not a misunderstanding. Sandbox limitation, no explicit input-output pins. Correct, the sandbox does not give you named I/O pins. Everything is implicit wiring between placed components. This does not force you into the component factory yet, but it does force a clarification of roles. There are two viable interpretations of sandbox in Turing complete. Pure playground, wires only exist as connections between placed blocks. Factory-backed sandbox, you place instances of factory components and wire them. Phase 0 requires named, global control rails. That means, yes, the first minimal phase harness must live in the component factory, but only as infrastructure, not as a reusable black box abstraction. This is one of the rare justified exceptions. However, you must treat this factory component as transparent, inspectable, mutable, not a final product. Think of it as defining clock, not STD, vector. 2. What exactly goes into the component factory? Minimal. You are not building a clock component. You are building a phase rail provider. Bit width. All signals, 1 bit. Never 64-bit. Never buses. Inputs. You need some way to drive phase transitions. Minimal options. Option A, manual, best initially. Phi 1 in, 1 bit. Phi 2 in, 1 bit. Option B, derived, later. Tick, 1 bit. Start with option A. Outputs. Phi1. Phi2. Phi0, strongly recommended. Free. Logical behavior, exact, no interpretation. In a copy could Phi1 equal to Phi1 in. Phi2 equal to Phi2 in. Phi0 equal to Phi1 and Phi2. That's it. No clocks. No edge detection. No storage. No timing magic. If you later want automatic alternation, you add logic. You do not change this contract. 4. Dot graph of the circuit, textual, concrete. Here is a precise dot graph describing the minimal phase 0 harness. Rust copy coded to graph phase rails. Ranked or equal polar. Inputs. Phi1 in. Label equal to Phi1 in, 1 bit input, ship equal toe box. Phi2 in. Label equal to Phi2 in, 1 bit input, ship equal toe box. Outputs. Phi1. Label equal to Phi1. This is not illustrative, it is exactly the topology you want. 5. How this is used by other components, mechanically. Later components do not instantiate this. They simply connect their Phi2 input to the global Phi2 rail. Gate writes with it. Example invariant inside a latch register. In a copy code write effective equal to write-enable and Phi2. If someone wires storage without Phi2, that is a structural violation, not a usage mistake. 6. Why this belongs in the factory despite earlier advice. Earlier, I said don't start in the factory, that was about abstraction freezing. This is different. You need named rails. Sandbox cannot name rails. Factory is the only place names exist. So use the factory here as a namespace mechanism, not as an abstraction boundary. This is subtle but important. 7. What you should not do yet. Do not add flip-flops. Auto toggle phases. Collapse this into clock. Hide phase error. Generalize bit widths. Phase 0 succeeds if it feels almost too simple. 8. Mental checksum. If someone later asks, why didn't this register update? You should be able to answer. Because Phi2 was low, and I can point to the wire. If you can't point to the wire, phase 0 failed. This is the foundation everything else stands on.
I don't understand. Let me think about like how to verify this. I think probably like might not be a good idea to use ChatGPT to figure out the details. I think I have to come up with the circuits. Maybe we should go over these things. I need to map into something that I know is a real system. I think that's probably a better idea. I remember like some time ago, maybe I still have the code, but I don't remember really well. I was going over with ChatGPT on actual Verilog and not the Turing Complete, and I was building a system to understand. I was trying to rebuild UART, which is a protocol of communication between different parts of the hardware on Verilog. So maybe I should do something like that, where first I ask like what are the main components. I use ChatGPT and research based like on search engines to figure out the schematics, the actual schematics of the real thing. Obviously I have a bunch of books here and stuff that has diagrams, but the problem I have with these diagrams is that they are not, a lot of the times they are not the real thing, obviously. There are simplifications. There are some, like the official websites and some places that have the real schematics. But like the real schematics is a 3D, very complex thing. So I don't want that either. Just want the middle ground where I can, some variation of this, where I can start from this and then go figure out what are the minimum components I can build, and then build the abstractions one by one from the smallest parts to have the bigger systems. Because the problem is like there's entropy on ChatGPT, so it starts to deviate from the overall vision. And I have to understand, like I can't let it guide me through the steps because then it's like gonna go off track. I need to understand the vision and make sure that ChatGPT follows. Limit. This. Or you link. So I think that this is probably used outside once you have the components already. So on the sandbox, you use this. So probably the easiest way to validate is just to look into the inputs or manually write the truth table that I want. Because like, if I understand from the thing here, it just wants me to build an AND gate. So I don't get why he wants me to do this now. This is something else that I don't understand. They say this custom component cannot be used as it has no area. So what the fuck does that mean? Oh, it's because of the outputs. searching for the schematics as well of the circuits. Maybe that will help. Yeah, I think that I'm gonna do this off stream. I'm going to ask ChatGPT, or maybe like create a. Yeah, I'm gonna use ChatGPT to research and then bookmark the sites that have official schematics, so that it becomes easier to search for them each time. Maybe I should have done this from the beginning. Maybe I should rethink it, like redo the markdown and start from the problem is like I remember some time ago trying to search for the real schematics, and all I could find from what I remember is just the official manuals of assembly and stuff like that, and they are not very well organized. Like they don't have the actual like, they have the schematics on some places, but it's just in the middle of the thing and it's surrounded by text. It's kind of annoying to search on that format. I was looking more for, and obviously is also more annoying to keep track of because one more external thing to think about. It's just more convenient to look into the markdown, look into the name of the gate, and then search later. Something else that I have to figure out is whether or not I can use one sandbox instead of the other. I'm pretty sure, yeah, the component factor I know, like the ones that I built here are gonna be available on the custom thing there on the sandbox. But I think you can't really use one sandbox into the other. So I was thinking about this because like here it doesn't seem that I can use the terminal there that I could use on the sandbox. So I was thinking about if I could build something like that shows the lines would be a lot easier to figure out if it is correct or not, to build a clock. But I guess I can use truth tables as well. Like this. With this.
Chapter 1. CMOS circuits. 1.5 Memory. Latch and register. Semiconductor memory, capable of storing large amount of information, are essential to all digital systems. In its simplest form, a single bit memory element can be realized as a latch or a register. A latch is a level-sensitive circuit for which the state of the output depends on the level of the clock signal. It passes the D input to the Q output when the clock signal is high for a positive latch, or when the clock is low, in case of a negative latch. This latch is then said to be in transparent mode. During the low state of the clock for a positive latch, the input data sampled at the falling edge of the clock is held, stable at the output. The latch is now said to be in hold mode. The input should be stable for a short period around the falling edge of the clock to meet setup and hold requirements. Figure 1.9 depicts a positive level-sensitive latch implemented using a 2-input multiplexer and 2 inverters. It has a data input D, a clock input CLK, and 2 outputs Q and Q, The output Q follows the input D when click tune foot. When click toe 0 feet, the D input is ignored, and the state of output Q is retained. Similarly, a negative latch passes the D input to the Q output when the clock signal is low. Figure 1.9, a CMOS positive level sensitive D latch.
Yeah, I think I'm starting to think that this is probably a better idea. I should research top-down. Like, I use GPT to search a real, I should think about which one I should do. So obviously, like when a real one is basically impossible to do manually, I have to do it with a software specialized for this, because obviously there's going to be billions of transistors, but the principles, you can simplify everything into the fundamental principles. And I'm pretty sure you can look into the schematics. I think NVIDIA probably has a bunch, and then AMD and companies like that, they provide the, I'm not really sure if they provide the schematics of the thing or just like the, but I do know that they provide the pictures and stuff like that. Maybe I should research from that standpoint, like first figure out which one I should try to reverse engineer, let's say, to build from scratch. Then research all the components that it uses, then build one by one from that point. Yeah, that makes more sense, because otherwise, like ChatGPT is not gonna be, because it doesn't have the context, it's gonna fluctuate like that, and it's gonna guide me through the wrong direction. So I should spend more time building this list here first, I think. But I think I'm gonna do that next time. I'm just gonna try to figure out if I understand what it wants me to do now.
You're getting stuck because you're interpreting phase 0 as a component to build, when it is actually a constraint you impose on all future components. The AND gate diagram was not the project, it was the minimum observable artifact that proves the constraint exists. Let me reset this cleanly and precisely. What this project is not. It is not build a clock component. It is not build an AND gate. It is not build something reusable on its own. If you try to package phase 0 as a normal reusable component, you are already doing the wrong thing. 2. What explicit two-phase clock discipline actually is, system level. At the system level, this project establishes a global temporal invariant. All architectural state updates occur only in phase PH2. All architectural state observations feed combinational logic in PH1. That's it. That single sentence is the project. Everything else, latches, registers, pipelines, is downstream of this rule. This is equivalent to saying in software terms, all writes happen in commit. All reads see a stable snapshot. No instruction can observe partially updated state. You are enforcing causal ordering, not building hardware for its own sake. 3. Why this matters for a large hardware system. Without explicit phase discipline, registers can become accidentally transparent. Combinational paths can feed back into themselves. State can update mid-computation. Bugs become timing dependent and unlocalizable. Out-of-order logic becomes impossible to reason about. With explicit phase discipline, every state transition is atomic at the architectural level. Pipeline stages become cleanly separable. Hazard reasoning becomes mechanical. Cycle becomes a real, inspectable concept. Debugging reduces to what phase was active. This is the difference between hardware that sort of works and hardware that scales in complexity. 4. What you are actually supposed to build in phase 0. Deliverables of phase 0, conceptual, not a single component. You are supposed to end phase 0 with a global understanding that there are 2 non-overlapping phases. All state updates are gated by PH2. A set of rules that every future component must obey. No storage without a phase input. No write enable that bypasses PH2. No combinational path from FITWU written state back into FAT2. A first concrete proof of the discipline. A latch or register that cannot update outside PH2. The AND gate was only to illustrate how violations are detectable, not the goal. 5. Where the component factory fits, properly. You use the component factory to build phase-respecting primitives, not the phase itself. Correct factory components for phase 0. You should build things like level-sensitive latch, PH2 gated. Inputs, D, write-enable, Phi2. Output, Q. Internal rule, Q updates IFF, write-enable and Phi2. Master-slave flip-flop. Built from 2 latches. Master active in PH1. Slave active in PH2. These use the phase discipline. They do not define it. The phase signals themselves are global wiring, not a reusable block. 6. But how do I test and debug this? You don't test phase 0 by running programs. You test it by attempting illegal temporal behavior and confirming it is impossible. Concrete examples. Test 1. Write outside PH2. Drive write-enable equal to 1. Keep Phi2 equal to 0. Toggle D. Observe, Q must not change. If it changes, your discipline is broken. Test 2, multiple updates per cycle. Toggle D multiple times during PH2. Observe either exactly one update at the boundary, or controlled transparency if latch intentionally. But this behavior must be understood and intentional. Test 3, combinational feedback. Try to route QD through logic. Confirm that updates only occur on phase transition. You are debugging time, not values. 7. Why there is no phase error output in the factory? Because error detection is a development scaffold, not an architectural feature. In real CPUs, you don't ship assertions, but you design with them. In Turing complete, you simulate that by temporarily adding LEDs, halts, or probes, then removing them once the invariant is trusted. The important thing is that you reasoned about violations, not that the final component exposes an error pin. 8. Reframing your confusion. This is the key insight. You are asking, what exactly am I supposed to build? The answer is, you are supposed to build the rules that future components are not allowed to break, and then encode those rules into the structure of your component so breaking them becomes impossible. Phase 0 is successful when later components feel boringly deterministic. Timing bugs stop being mysterious. Every state update has a single visible cause. If phase 0 feels underwhelming in terms of circuitry, that's correct. Its value compounds exponentially later. Once you build your first register and realize it literally cannot misbehave temporally, you'll feel the payoff. If you want, the next step to make this concrete is walking through the exact internal wiring of a PH2 gated latch, and why it enforces the discipline by construction.
I think I understand where it's coming from. Like the point of the first level is not to test, not to build a specific gate. It's just to teach this invariant property of computation that you have to enforce that the system is either writing or reading from the state, because that's gonna go into everything else, I think. It's basically combinational logic determines the structure of the state of each state, and then the clock is gonna determine the transition between them, I think, which is this clock that is telling me to do. But the part that obviously I'm struggling with is like, how do I put this into practice? Like, how do I know if I built this correctly? Yeah, so it's basically this thing here, I think that's is trying to make me do a variation of this without building the combinational logic or memory necessarily. So the question is, and this is the part that this is the reason why I'm asking about the counter, because like how am I going to keep track of the time if there is no time here? That's the thing. I can use this clock as well, this Unix time. I'm gonna ask about this as well. But this is something that I also struggled with. I still struggle now, is understanding which gate the schematics is referring to. I'm not really sure how to clarify this on, because I don't know the name obviously, and I can't copy the schematics. Just ask based on the name. I think that's probably an OR or an AND. each one of this? Not, I don't know for sure. I don't remember. Oh, this is another thing that I want to clarify. So I want to clarify how ChatGPT is thinking about the time, like on the overall system, how it's gonna work. Because this is something that is very complicated as well. Because the way that they teach on tutorials is basically you have one clock and then the computer works based on that clock. But Honor Mutlu has some lectures where he explains and he talks about this as well. In real systems, you have multiple different clocks because of the latency. Latency is the amount of time that it takes the signal to go from one place to the other. So because of the latency, these different subsystems of the hardware become desynchronized. So you need to have a system that like synchronizes the clocks internally. And there's also this is also relevant to the networking, which makes it more complex as well. There are protocols on networking uh, because the different hardwares are gonna have different clocks, obviously. So you need to send the clock signal as well. And there are different protocols to send not only the data but the clock, and then the hardware. I think it has some structure to decode the information, which I think is a phi lock or something like that, phase lock. It's basically, from what I remember, there's a video where a guy talks about this. There's basically a loop where you make sure that the phase is right or something like that. I don't remember the details very well, but I do think it is done on the hardware to synchronize the clocks. It's probably done on the NIC hardware network interface card. But I'm gonna review this when it gets time to build this stuff as well. On everything, whatever.
This question finally hits the real difficulty. I'll answer it at the level you're actually asking: how to make time concrete, observable, testable, and Turing complete, and how that maps to real hardware. I'll proceed in strict layers, because mixing them is what's causing confusion. 1. First, erase real time from your head. The time gate, Unix microseconds, is not relevant to this project. Real hardware does not reason in wall clock time. It reasons in logical cycles. In CPUs, there is no notion of microseconds internally. There is only clock edges, phases within a clock, ordering constraints. So for this entire ledger, ignore the time gate. It models environment time, not architectural time. Architectural time equal to cycle count, not seconds. This is why phase 0 includes clocked invariant probes and cycle counter. That counter is logical, not physical. 2. What time means in your system. You must separate 3 distinct notions of time. A. Simulation ticks, game engine. Invisible. Unreliable. Not architecturally meaningful. B. Architectural cycles, what you define. Discrete. Countable. Observable. This is what CPUs use. C. Phase within a cycle. PH1, PH2. Subdivision of B. Enforces causality. You are building B and C explicitly. 3. How real hardware does this, mapping. In real hardware, a crystal oscillator produces a clock. Internally, designers reason in rising edge, falling edge, or multi-phase clocks. But nobody reasons in seconds. They reason in at cycle n, before the edge, state S is visible, after the edge, state S exists. You must recreate that abstraction inside Turing complete. 4. The key realization: this unlocks everything. PH1 and PH2 are not driven by time. They define time. You do not ask what time is it. You ask, which phase am I in? Has the cycle advanced? This is why you felt lost trying to measure time. You don't measure it. You count transitions. 5. How to make time observable in Turing complete. Now we get concrete. 5.1. You need a global cycle counter. This is where the provided counter component is used. Use a 1 cycle per PH2 increment rule. That is the invariant. Cycle counter wiring. Counter width, 8 or 16 bits, doesn't matter yet. Increment when phi2 equal to 1, and cycle advance equal to 1. Output cycle number. This counter is your architectural time base. 6. How PH1, PH2 are generated, finally concrete. Minimal, correct implementation. You need 1 bit of state that toggles. Call it phase. Phase equal to 0, PH1. Phase equal to 1, PH2. Implementation. 1 bit register or latch FF once you build it. On each global tick input. Go copy code phase, equal to not phase. Then decode. In a copy code Phi1 equal to not phase. Phi2 equal to phase. This is exactly how 2-phase clocks are modeled. No wall time. No Unix time. No delays. 7. How you test the temporal invariant. This is the core. Now the important part. What is the invariant? Architectural state may change only on PH2. So to test it, you deliberately try to break it. TERS, concrete test harness. You can build this now. Components involved. Phase generator, 1-bit toggle. FINAS, PH2 decode. A test register or counter. A cycle counter. Probes, LEDs, outputs. Test 1, illegal write during PH1. Wire. Test register writeable equal to 1, constant. D input toggles continuously, or driven by another counter. Register gated by Phi2. Procedure. Step simulation, tick by tick. Observe. During PH1, output must not change. During PH2, output may change. If it changes during PH1, discipline violation. Test 2, exactly 1 update per cycle. Wire. D equal to cycle counter. Retainable equal to 1. Expected behavior. Register updates once every 2 ticks. Register value equal to previous cycle number. This proves no double write. No mid-cycle transparency. Test 3, feedback stability. Wire. Ruscopy codec adder, D. Without phase discipline, this oscillates or races. With discipline, stable for entire PH1. Commits once in PH2. If you see oscillation, temporal model is wrong. 9. Where this sits in your ledger. Now your phase 0 checklist makes sense. Explicit 2-phase clock discipline. PH1, PH2, plus global cycle counter. Level sensitive latch. Must obey PH2. Edge triggered, FF. Built from PH1, PH2 latches. Clocked invariant probes. Counters plus comparators checking invariance. Everything downstream depends on this. 10. How this scales to the full system. Later, when you have pipeline stages. ROB. Register files. Caches. They all share the same PH1, PH2 rails. Share the same cycle counter. Advance architecturally in lockstep. Even if memory stalls. UO, execution reorders. GPU lanes diverge. Commit still happens in PH2. That's how real CPUs stay sane. 11. Final mental model, lock this in. You are not synchronizing to time. You are constructing time. pH1, pH2 are the smallest unit of causality. The counter is your notion of now. Everything else is constrained by that. Once you internalize this, phase 1 to 6 becomes straightforward mechanics instead of guesswork. If you want, next we can design the exact latch schematic that obeys this model, or build the cycle invariant probe component explicitly.
I understand what it's saying, just not really sure about how to do this. I should have two different states, and then the counter determines the sequence, and the state is the whole thing. Don't remember how to do this. Yeah, I'm not really sure if I should do this. Is it like I already did the levels, and on the level they do the half adder, full adder. But maybe it's good to do it again just to solidify. Because on these ones, I think I just looked at the solution. But the problem is that I don't think I'm gonna remember if I have to do it again. It's gonna be the same thing. I remember the concept, but I'm not gonna remember the specifics. It's just basically using the XOR to do the sum. The XOR captures the difference, which is a sum in binary. So the way that I'm thinking about now from a physics perspective is that the XOR captures interference patterns on waves, and the AND accumulates the result of the interference. So the AND will be like a constructive interference, and that's why you create it possible to create an integer from XOR and AND gates. You're basically capturing the interference between the signals with the XORs, and then you're using the AND gate to accumulate that to the carry. Yeah, these ones I don't think two complements as well. There is a level. I think that's you do this. Basically inverting and then you add one to the number. So I think this is gonna be like the full adder. And then you just use a NOT on one of the inputs and a byte on the other input. And that's it, pretty much. And then you add one, yeah. So you use the NOTs and add, yeah. So it's probably not that interesting as well. Maybe subtraction via addition is interesting. And these ones I also, I think I already did on the levels. I'm probably gonna go back. Like I think it was a mistake to use GPT to do the levels here, or to do the projects. Probably better to, because what I'm aiming for is to try to build the real systems from scratch in order to clarify how they work in practice. So what I should have done probably in the beginning is to do the research first to find like something that is real and that is used in practice, as schematics or something like that. Then go from the begin with the end in mind, basically. And from that point, I deconstruct and build the levels until I get to that point where I have the real system. I think I'm gonna try to build like a real hardware on Turing Complete. So each component, each subsystem becomes a component. And then on the sandbox, you have the entire hardware. That's the idea.
Short answer first, then the structure underneath it. Yes, you should think in cycles. Yes, phase 0 is a two-state cyclic system. No, this does not break project ordering. No, you should not use the Unix time gate. Using the built-in clock is acceptable only as a stimulus, not as time. Now the careful explanation. 1. Cycle versus linear. This is fundamentally cyclic. A linear input-output model is combinational logic. Phase 0 is explicitly not combinational. What you are defining is a repeating cycle with an internal structure. Formally, copy code. Finas, PH duo, Finas, PH duo. This is a finite state machine with two states and a transition relation that loops forever. There is no terminal output. There is no completion. There is only advance. This mirrors real hardware. CPUs do not finish. They advance architectural state one cycle at a time. Even halt is just a stable state under the same clock. So, think cycle, not flow. 2. What phase 0 actually builds, precisely. Phase 0 builds one thing only. A globally shared notion of which half of the cycle the system is in. That notion must be explicit, inspectable, shared by all later components. This is the root temporal coordinate system of your machine. Nothing computes without it. 3. But you mentioned registers, isn't that out of order? This is an important subtlety. You are not building your register yet. You are allowed to use one minimal state holding element to bootstrap time itself. This mirrors reality. Real CPUs use latches to define clocks. You cannot define sequential behavior without some state. In your ledger, this is why phase 0 contains clocked invariant probes and cycle counter. Those probes require some state. 2 key points. Bootstrapping state is allowed. Architectural state is not. Using the built-in counter or a temporary 1-bit register is acceptable only to define time, not to define architecture. Later, when you build your own registers, you will replace them or validate equivalence. This does not violate ordering, it establishes the coordinate system the ordering relies on. 4. Clock gate versus counter versus tick. Clarify the roles. 4.1. The built-in clock gate emits a periodic signal. This is a stimulus, not time. Think of it as the crystal oscillator pin. It is acceptable to use it as advance request, toggle trigger. It is not acceptable to treat it as architectural cycle count, phase itself. 4.2. The counter counts architectural cycles. This is your notion of now. The counter increments once per full cycle, not per phase. 4.3. The relationship. One clean model. SQL copy code clock, tick, phase toggles. Every PH2, cycle counter increments. This mirrors real hardware exactly. Clock edges drive phase changes. Cycles are counted logically. 5. The minimal phase 0 machine exactly. Yes, stripped to its essence, phase 0 is one 1-bit state that toggles forever. Let's define it rigorously. State. Copy code phase, 0, 1. Interpretation. In a copy code phase equal to 0, PH1. Phase equal to 1, PH2. Transition. Sharp copy codon tick. Phase, equal to not phase. Derived signals. In a copy code phi 1 equal to not phase. Phi 2 equal to phase. That is the entire temporal engine. Everything else you build later consumes phi 1, phi 2. 6. How this becomes observable and testable. You test time the same way you test logic, via invariance. Fundamental invariant. Architectural state may change only when phi 2 equal to 1. So you build something that tries to violate this. Concrete test harness. A counter or latch whose write enable is permanently 1. Its data input changes every tick. Its write path is gated by phi 2. Expected behavior. During pH1, output stable. During pH2, output updates exactly once. If you can step the simulation and see this, you have validated phase 0. You are not testing a component. You are testing a law. 7. Global versus local timing, critical clarification. There is exactly one global cycle timeline. Components do not have independent clocks unless you explicitly design CDC later, you won't, initially. All components. Share phi 1. Share phi 2. Share the cycle counter. Local timing logic only exists for stalls, enables, gating. But commit time is global. This is how real CPUs work. Thousands of local enables. Architectural clock. 8. Answering your final. Is this the whole circuit? Question. Yes, conceptually. Phase 0's core is a two-state cyclic machine. Plus observability. If it feels too small, that's correct. Its importance is not size, but what it forbids. No mid-cycle writes. No time ambiguity. No accidental transparency. No, it depends on the simulator tick. Once this is in place, every later phase becomes structurally constrained instead of informally disciplined. 9. Lock-in mental model. Keep this invariant burned in. You are not simulating time. You are defining it. Clock gate, stimulus. Phase bit, temporal state. Counter, architectural now. pH2, the only moment the world is allowed to change. With that in place, your ledger ordering is sound, and the rest of the system will compose cleanly. Good, now we're at the actual mechanical blockage. I'll be very concrete, and I'll also correct one key misconception that's blocking you. 0. Critical correction. This is the unlock. You cannot build a cyclic system in Turing complete using pure gates. Circular behavior requires a stateful element. The game is correct to forbid gate output, gate input loops, because that would be a combinational loop, which is undefined. Cycles in hardware exist only through state. So, not gate feeding itself. And/or loops. Gate, register, gate, register. This is exactly how real hardware works. So yes, you must use a stateful component to create the PH1 PH2 alternation. That stateful component is not an architectural register. It is the clock state itself. This does not violate ordering. What is the minimal allowed state? You need exactly 1 bit of state. You can implement this with any of the following. 1-bit register. 8-bit counter, using only bit 0. T flip-flop, if available. Since you explicitly said you have an 8-bit counter, we'll use that. 2. How the 8-bit counter is used, precise. The counter is not measuring time. It is hosting the phase bit. Counter configuration. Width, 8 bits. Use only bit 0, count 0. Increment every tick. Ignore higher bits. Then, in a copy code phase, equal to count 0. Phi 2 equal to phase. Phi 1 equal to not phase. That's it. This is a textbook clock divider. 3. Inputs and outputs, explicit. Inputs. You need one external stimulus. Tick, 1 bit. This comes from the built-in clock gate or a manual button. This answers your where does motion come from question. Outputs. You expose. Phi 1 1 bit. Phi 2 1 bit. Optionally, also phase for debugging. These are global control rails, not results. 4. How the counter is wired, exact. Counter pins, as provided by the game. Increment, 1 bit. Overwrite, 1 bit. Overwrite value, 8 bits. Output, 8 bits. Wiring rules. Increment, equal to tick. Overwrite, equal to 0. Overwrite value equal to 0. Output equal to phase counter, 7. 0. Extract. Phase equal to phase counter, 0. 5. No illegal circular wiring involved. Notice carefully. The counter's output does not feed its input. The counter advances only because of tick. The cycle exists across simulation ticks, not within the schematic. This is legal sequential feedback, not combinational feedback. 6. Complete dot graph, fully specified. This is the concrete schematic you asked for. Rust copy coded a graph phase 0. Ranked are equal toller. Inputs. Tick, label equal to tick, 1-bit input, ship equal toe box. State. Counter, label equal to 8-bit counter, shape equal toe box. Gates. Not phase, label equal to not shape equal toe box. Outputs. Phase label equal to count 0, ship equal to WEPS. Phi 1, label equal to phi. This graph has no illegal loops. Exactly one stateful element. Explicit phase rails. This will compile in Turing complete. 7. What happens when you tick the simulation? Tick by tick behavior. Tick counter phase if Phi 1, Phi 2. Quindecillion 10 undecillion 100, decillion. Octillion, 101 septillion, 200 sextillion. 10 quadrillion, 10 trillion, 300 billion. That is your two-phase cycle. 8. How this becomes a testable temporal invariant. Now connect any test storage like this. In a copy code write effective equal to write-tenable in Phi 2. Then observe. During Phi 1, writes are impossible. During Phi 2, writes are allowed. You step the simulation and watch this happen. That is how you play it tick by tick. 9. Final alignment with your ledger. Satisfies. Explicit two-phase clock discipline. Prepares ground for latches, flip-flops, cycle counters, invariant probes. You have now made time concrete inside the game. 10. Lock this in. If you remember only one thing from this message, remember this. Cycles in hardware exist only because state exists. Gates never make loops. State does. Once this clicks, the rest of your project becomes mechanically straightforward.
Yeah, this is not very good because I don't understand, like, I can do it, what is, like, alluding to, but I don't understand the specifics of what it means. So I think it's probably better to do what I said, where I begin with the end in mind, and then I just search, like I organize the, it's probably, I think I'm gonna do this off stream. I'm going to search for a real hardware, then I'm gonna break down the components that it uses, and then I'm gonna get the schematics and clarify what gates are used on the schematics. Then I build from the schematics, I use ChatGPT to build each component. I think that's better. Because otherwise it's gonna be too vague, and I'm gonna waste a bunch of time just trying to decode what ChatGPT wants me to build. Not very good. 'Cause here, like, it doesn't make any sense what it says here. Like, what the fuck this is supposed to be? Base equals count 0. And it could be a variation of things. And obviously there's a lot of things I can do there. But I don't understand like what it wants me to do. Here it doesn't have any output as well. The problem is that like based on what it's saying, this is supposed to be an exercise and then and not a component that I'm going to reuse somewhere else. But then it's related to timing, which might be related to stuff that I like is unclear. It's kind of ambiguous whether or not I'm supposed to build this to use later or not. Because that's the problem. I don't know how it's gonna fit on the big picture. That's the issue. Like I think that something like this that I'm doing here would be like similar to what it's telling me to do. The clock determines which one is active. And then I would have two outputs, I think. Then on the external system, you would be able to differentiate the state based on the output you connect to. And then obviously there probably are a bunch of different other ways you can do this, but so I think I'm gonna stop here. I'm gonna use GPT offstream to research, and then I'm gonna build. I'm gonna maybe I should put the files of the schematics, the pictures inside of this project here, and go from the if this doesn't output anything, this doesn't have the enable. I think I could put a switch here to do this, but like I said, it's not very clear what exactly I should do with this. Yeah, I think this picture here is probably the best one that describes what it wants me to do. What ChatGPT is trying to make me do. Send inputs, and then you have combinational logic, and then you have the output. You have combinational logic, memory, then the output. The memory determines what happens. Then obviously it's unclear what the combinational logic should be. Yeah, so I'm gonna stop streaming now. Next time I'm probably not really like I want to avoid spending a bunch of time doing stuff off stream that's related to streaming. So I might next time just research this on stream. But I do think that it's probably better to clarify the direction first. Like I have to manually think about the steps instead of letting GPT do it. Otherwise, the ChatGPT part should be only helping me translate the schematics into the Turing complete. That's the thing. Or the parts of researching where to find the schematics and how to make sense of what each symbol represents on the schematics. Because I think that this is gonna be a lot easier to think about. If I think about what system I should build in the end, it's gonna be easier to build each component. Yeah, so if I don't research this offstream, the next time I'm just gonna use ChatGPT to research, try to find the schematics. I think first I'm gonna try to clarify what project he thinks is the best to do, like the final project. Actually, I'm gonna think about this. But probably data path should be one that is interesting, and memory, cache coherence, stuff like that should also be interesting. Then the NIC and digital processing things, analog to digital converter, stuff like that. So I'm probably gonna come up with an order that I think makes sense based on what I'm curious about. Then I'm gonna clarify the schematics. I might do this on stream next time. Just clarify the use ChatGPT to figure out where I can find the schematic. Once I have the schematics, I try to translate the schematics into Turing complete. Yeah, so see you next time.